Alright, so this is a sort of short review of some basic trigonometry for students in the Math 1410 in Linear Algebra course at the University of Lethbridge for spring 2017. We're just going to quickly go over some of the basics from trigonometry that you should have encountered in high school, but it's possible that it's been a while and you're a little rusty, and it never hurts to have a recap of some of these things. So the trigonometry that we're interested in is the trigonometry of the unit circle. You can also talk about triangle trigonometry, dealing with sine and cosine in terms of opposite over hypotenuse and adjacent over hypotenuse for right-angled triangles and this sort of thing. But the sort of more fundamental trigonometry, the stuff that's of interest if you're doing mathematics, is trigonometry as defined on the unit circle. So the unit circle in the Cartesian coordinate plane is defined as the set of all points, let's say xy, so let's say here's a point xy on the unit circle, satisfying the equation x squared plus y squared is equal to 1. And so the triangle trig, I guess, in some ways is lurking in the background here, because once you have that point, there is a little triangle that you can draw. And of course, the x and y coordinates of that point are simply giving you the width and the height of the triangle. So this side of the triangle has length x, this side of the triangle has length y, and if you remember your distance formula, the length of the hypotenuse is just the length of the point xy from the origin. That's equal to 1. That's where this expression comes from. That's where the equation of the circle comes from. It's simply the statement that you're interested in all points whose distance from the origin is equal to 1. Alright, now there are a number of points that you can easily plot on the unit circle, but there are not that many. If you set y equal to 0, then you're just left with the equation x squared equal to 1, and there are two possible values of x that satisfy that equation. Either x is equal to 1 or x is equal to minus 1. Similarly, if you set x equal to 0, then you have to have either y equal to 1 or y equal to minus 1. Now, most of the other points on the unit circle are going to look fairly complicated. One of the things that you can discern is, well, you do know that we're dealing with squares of real numbers here, and we know that whenever you square a real number, right, say x for example, the square of a real number is never negative. It's always at least 0. And since x squared is bigger than or equal to 0, that means that if you want to know what possible values y squared could have, well, y squared can't be any bigger than 1 because I'm adding x squared to it, and x squared can't be negative, so the biggest that y squared could be is 1, right? Because if y squared is equal to 1, there's no other possible value you could have for x other than 0. And of course the argument works the other way around, and you get these sorts of inequalities here. And now if you drop the squares, you think about, well, what are all the possible values for either x or y that fit between, that give me squares between 0 and 1? Well, of course, if x is between 0 and 1, that's going to work, but as you see kind of the left half of the circle over here, you could have negative x values, or the bottom half of the circle you could have negative y values. And so of course what happens is if we drop the squares, then x and y can be negative, but they can't be any smaller than minus 1. And so you're looking then, so certainly these are the only points that you can have where you have integer coordinates. These are the only possibilities for whole number coordinates. And then you might hope, well, maybe there are a number of fractional entries that you can come up with. But if you play around with that, you'll find that usually if you choose a rational number for one of the two values, because you've got to take a square root to solve for the other one is always going to end up being irrational. So for example, if x is equal to 1/2, so kind of halfway between 0 and 1, about right there. Well then, that would mean that x squared plus y squared would be equal to 1/2 squared plus y squared. And that's, of course, 1/4 plus y squared. And that whole thing is supposed to equal to 1. So y squared plus 1/4 is equal to 1 tells me that y squared should be equal to, if I subtract 1/4 from 1, I'm left with 3/4. And that tells me that y, well, if I take square roots, there are two possibilities. There's a positive root and a negative root. Square root of 3 over 2. And of course you expect two solutions, because I can take this value here where x is equal to 1/2, and I can extend that line up and meet the circle here. Or I could extend it down and I could meet the circle there, and this would be the point where x equals 1/2 and y is equal to root 3 over 2. Down here is where x equals 1/2 and y is equal to minus root 3 over 2. One of the nice things about the unit circle is that it is very symmetric, and so once you have one point on the unit circle, let's say a point in the first quadrant like this point x, y, there are going to be three other related points that you get just by flipping the signs, right? So you can flip the sign of the x coordinate, which corresponds to reflecting across the y-axis, and that would take you to this point over here. You get the point minus x and y. Or you could change the sign for the y-coordinate, which corresponds to reflecting across the x-axis, takes you down here. You get the point x and minus y. Or you can flip both signs, which corresponds to reflecting across the origin, taking you down to here. And you get the point minus x minus y. So because the unit circle is highly symmetric, points on the unit circle kind of come in these groups of 4. At least, points that are off of the axes tend to come in these groups of 4. For every point in the first quadrant, there's a corresponding point in each of the other quadrants, where the coordinates have the same absolute values, but possibly different signs. Okay, so once you've kind of have dealt with the unit circle, you've introduced the unit circle, you've talked about points on the unit circle, you want to connect this up with the idea of angles. So how do we measure angles? Well, remember that the basic idea with an angle is defined anytime you've got a pair of rays. So a ray is just a half line, so it goes off in one direction but not the other, and they meet at some common vertex. So anytime you have two rays, well then there's the angle is simply measuring the amount of rotation that is required to take one of the rays and turn it into the other. So I can measure, for example, this way. So I could measure an angle like that and call that angle theta. We tend to use this Greek letter theta to measure angles. Now, of course, we could measure it that way, but there's quite a bit of ambiguity here. There's not a unique angle that's defined. There's nothing stopping me from, measuring the angle this way. Maybe that's theta 1, that's theta 2, right? I could have gone in the other direction. I could have chosen to kind of, instead of measuring, counterclockwise from this guy to this guy, I could have gone the other way around. I could have decided to measure like so. That would define some other angle, let's say theta 3, or I don't know, maybe you want to get sort of really creative and do something like, you go out and you keep going and you go all the way around and you do a complete revolution, and then you go a little bit more until you end up at the other one. That would also define an angle. Maybe call that guy theta 4. So there are lots of different angles that you can define. But once we kind of tie angles into the unit circle and we introduce our trigonometric functions to measure these angles, we'll see that the results tend to always come out to be the same, however you choose to measure your angles. And there's a certain amount of standardization that we impose to make sure that everyone agrees on what we're talking about. Okay, so let's draw another unit circle. There we go. So the first convention that we make when we're dealing with the unit circle and measuring angles with the unit circle is that, well, every point on the unit circle is going to correspond to an angle. So if I've got my point xy here, That point is going to correspond to an angle. And the way I do it is I consider this point as defining a ray, like so, and the other ray is always the positive x-axis. And the convention is that you always start from the positive x-axis and then head towards your angles. So I go like so, and I measure this angle theta. Okay, and again, that doesn't completely resolve the ambiguity, because I could measure this counterclockwise angle like so, but I could also choose to go around. I could choose to go around like this, and I could measure that angle like so, or I could do, as I had done before, I could choose to do more than one revolution. I could choose to go all the way around and come back, you know. So any sort of angle like this would work, as long as I begin on the positive x-axis and I rotate around and I end on the ray defined by the point that I'm interested in. Any one of those would be an acceptable angle for that particular point. Now, so all of these angles, the word that you often use when you're dealing with these angles that all kind of define the same point on the unit circle, you sometimes call these coterminal angles. And every coterminal angle, you can probably guess that every coterminal angle is going to differ by one complete revolution, right? And now there's a bit of a question of clockwise versus counterclockwise here, but let's say any two counterclockwise angles, the difference between any two counterclockwise angles is always going to be some multiple of a complete revolution. Could be one complete revolution, maybe 2, 3, 4, some number of full trips around the circle plus a little bit more to end you up at that point. And so what we're going to do is we're going to define functions. We're going to define functions of an angle. And of course, you can sort of see that once you've chosen your angle, right? Once you've chosen your angle, then that angle gives you a point on the unit circle, because you simply draw the ray that kind of gives you the angle you're interested in. And then you get two numbers. You get x and you get y. So there are two numbers associated to every angle. And so that means that there's a way of defining two functions. One function given by the x-coordinate and another function given by the y-coordinate. The only other thing that I want to mention before we move on, just as a way of warning, if you like, is that in pretty much any mathematics class that you're going to take, angles are always measured in radians. Okay, so the radian measurement, you'll probably recall, assigns an angle of 2 pi to a complete revolution. So in radians, 1 full revolution is equal to 2 pi radians. If you were working in degrees, a full revolution is defined to be 360 degrees. The nice thing, the reason why people like working in degrees, the degree measure is convenient because 360 has a lot of divisors. So, if you want to talk about a half revolution, 360 is divisible by 2, you get 180 degrees. You want to talk about a third of a revolution, you divide by 3, you get 120. It's still a whole number. A quarter of a revolution, 90 degrees. A fifth of a revolution, a sixth of a revolution. All of these come out to be whole numbers of degrees, and that's one of the reasons that degrees is convenient. So why are radians preferred when degrees seem to be so convenient? Well, one of the things that we'll see, and we'll discuss this when we talk about the values for the sine and the cosine functions, is that with radian measure, so a full revolution is 2 pi radians, so a half revolution is going to be pi, going, so 180 degrees starting here and going, halfway around the circle. Gets you to an angle of pi. A quarter of a revolution is half of that, so half of pi, so you get pi over 2 for a 90-degree angle. Half of that again would be pi over 4 for a 45-degree angle, and so on. And there are certain standard angles that all are sort of a form, so the standard angles that we're going to talk about are these ones like you'll have you know, pi over 6 and pi over 4 and pi over 3 and pi over 2, and all distinguished by this number that shows up in the denominator. And we're going to see that that actually makes it really easy to identify you know, these related angles, in the sense, you know, on the previous slide where you would have you know, these points, one point in each quadrant, where the only difference between them is the signs of their coordinates. That that's something that shows up when you're dealing with radian measure. If I have an angle pi by 3, but I'm actually interested in an angle maybe over in, say, the third quadrant or the fourth quadrant, or you know, something like that. Well, in quadrant 1 my angle would be pi by 3. In quadrant 2 it's 2 pi over 3. In quadrant 3 it's 4 pi. In quadrant 4 it's 5 pi over 3. The denominator is always a 3, and it makes it easier to recognize things. The other reason why working with radians is nice is that in radians, an angle theta corresponds to, you can kind of measure the length of this chunk of a circle, right? So this piece of the circle here. So if you cut that piece of the circle out and you straightened it out and you measured how long it was, the length of that piece of the unit circle is in fact equal to theta, and this gives you a way of identifying angles and numbers, and that's kind of the starting point for identifying your trig functions, not as functions of an angle but as functions of a number. Okay, so speaking of trig functions, let's introduce those guys. So again, we'll start with our unit circle sitting in the xy plane. There it is. And we plot a point on our circle, so we plot our point xy. Any such point defines an angle theta, or if you like, the angle theta defines the point. And well, the two trig functions, sine and cosine, are defined quite simply. The cosine function is denoted by cos theta, and that's simply the x-coordinate of this point, right? As soon as you define theta, you get the point, and cos theta is simply the x-coordinate of that point. The sine function then is the y-coordinate of that point. And of course, once you realize that, you get probably the best known of all the trigonometric identities, remembering that the equation of our unit circle is x squared plus y squared is equal to 1. Well, that tells you automatically that cos squared theta plus sine squared theta has to always equal to 1. Okay. The only other trig function that we'll make use of, I mean, there are 6 different trig functions that you can consider. The only other one that we'll probably talk about would be the tangent function. Tan theta, which is defined to be sine theta over cosine theta. So it's y over x as long as you're not on the y-axis. So the tan function is not defined at the top or the bottom of the circle, but it's defined everywhere else. And one of the things that you might remember about the tangent function, y over x, it's like rise over run. This gives you essentially the slope of this line segment that you use to measure the angle theta, right? So the tangent function is sort of like slope. But for the most part, we really just care about the sine and the cosine functions. All right. Now, you want to be able to evaluate these functions, and evaluating them at any old point on the unit circle is quite impossible, to be honest. And if you kind of, I mean, nowadays everyone has, if you've got a scientific calculator, you've got access to a computer, you've got devices that will calculate the value of sine and cosine for any old angle that you want to plug in. Um, if you go back, you don't even have to go that far back, maybe 50 years ago, before pocket calculators really were in existence, people used to have to lug around these books, these huge books with these tables in it containing values of the sine and cosine functions for different angles of theta. And the reason they had to carry those around is that there are very few values of theta for which we can easily evaluate the sine and cosine functions. And we'll list those off. So there's theta equal to 0, corresponding to the point 1, 0. So remembering that cosine is the x-coordinate and sine is the y-coordinate, you can immediately conclude that, well, cosine of 0 must be equal to 1. Sine of 0 must be equal to 0. The next angle for which a sort of exact value is easily determined is the angle pi over 3. So if theta is equal to pi over 3, the coordinates of this point, this turns out to be when y is equal to 1/2. So x is equal to root 3 over 2. Y is equal to 1/2. You can work out that those are the coordinates there. And so you get that cosine of, oh, sorry, let me make a correction here. 3 is the wrong denominator, isn't it? Pi over 6, it's the smaller of the two. We'll mention that in a bit. It's easy to sometimes get some of these angles mixed up, so we'll talk about how do you keep that straight and make sure you don't make a mistake like I just did. So cosine of pi over 6, that's root 3 over 2. Sine of pi over 6 is equal to 1/2. The next angle that's easy is the angle where x and y are the same. So if x is equal to y, so slope is equal to 1, so the x and y values are the same. This corresponds to an angle of pi over 4. And setting x equal to y, you can quickly work out that x and y both have to be equal to 1 over the square root of 2. And by the way, if you had a teacher in a high school who was really a stickler for this sort of thing, 1 over the square root of 2, if you really want to, you could rationalize. You could write this, you multiply top and bottom by root 2, and you write this as root 2 over 2. So if you want to, you can write 1 over root 2. If you prefer, if you had it really drilled into your head and you have to write it as root 2 over 2, you can do it that way. It doesn't actually matter. Nobody actually really cares which way you write it down. It doesn't make any difference. In fact, the only reason why historically people always rationalized, they made sure that if you had a square root, that it was in the numerator and not the denominator. The reason why you had to do this was that this is how you calculated values on a slide rule. These days we don't use slide rules, so we don't really have to worry about this. So you can rationalize if you want to, but there's no real need. Okay. So the other point, well, once you've worked out pi over 6, so this guy here, which makes an angle of 30 degrees with the x-axis, there's this corresponding angle making an angle of 30 degrees with the y-axis, and so there's some symmetry about the line y equals x corresponding to theta equals pi by 4, and you might recall that the way you resolve this is you just sort of swap the x and the y coordinates. So the coordinates here, x is equal to 1/2 and y is equal to root 3 over 2, and so this is the angle pi over 3, and that tells me that cosine of pi over 3 must be equal to 1/2, and sine of pi over 3 must be equal to root 3 over 2. The last one that we'll mention is up here at the top. When theta is equal to pi over 2, so a right angle, a 90-degree angle if you like, if you want to work in degrees. That's where x is equal to 0 and y is equal to 1, so that one again is pretty easy. We have that cosine of pi over 2 is equal to 0, and sine of pi over 2 is equal to 1. And now the main place where people tend to kind of get tripped up when they're evaluating the sine and the cosine functions is, they get tripped up with the sort of symmetry that you see here, right, between, so for example, between theta equals 0 and between theta is equal to pi over 2, you can see that the coordinates are swapped, and so the values are swapped between sine and cosine. And the same thing goes between pi over 6 and pi over 3. Again, the two values are swapped. You alternate between the root 3 over 2 and the 1/2. The easiest way to keep track of things and remember which values you should be plugging in is just to remember that these are coming from points on the unit circle. And if you remember that cosine is always the x-coordinate, you remember that sine is always the y-coordinate, and you remember where on the circle you are if you plug in, say, theta equals 0 or pi over 2 or pi over 6 or something like that. Between pi over 3 and pi over 6, right, 6 is the larger between 3 and 6, and so theta equal to pi over 6 is the smaller angle because you're dividing pi by a bigger number. And so with this smaller angle, you can see that you're kind of out here, you're around this point on the unit circle, where you're further out in the x direction than you are in the y direction, and so you expect that the x value should be bigger. You expect that the cosine value should be bigger, and of course root 3, that's around 1.7 something. It's bigger than 1, and so you can figure out which one you need to choose. Okay, so we'll say one more thing before we end, and that's just how to move beyond the unit circle. And this is something that's going to be relevant when we want to talk about the polar coordinate system. So we've got our trusty unit circle sitting here, and so that's a lot of help when we're dealing with points that are on the unit circle, if we're dealing with a point that's exactly 1 unit from the origin, but we may very well be dealing with some other point, some point way out here, right? Some point x, y. So how do you deal with such a point? Well, you can still draw the ray that passes through the origin, or from the origin to that point x, y. You can figure out how to draw that line. Once you've got 2 points, there's always a line between 2 points, and we know how to calculate the length of this line. Let's call that length r, because again we have the distance formula, so we know that x squared plus y squared here have to equal r squared, where r is no longer necessarily equal to 1, right? So this follows from the formula for the distance between 2 points in the plane, which says that the distance r should be the square root of, well, x minus 0 squared, so x squared, and then y minus 0 squared, so y squared. All right. So can I locate a point like that which is not on the unit circle? Can I still use an angle to locate that point? Well, I can, but I have to make use of this this value r that tells me how far away I am, right? So one way to think about it is that this point is on a much bigger circle. It's on a circle of radius r. Of course, I could also consider circles with radius smaller than 1, but for now we're drawing a scenario where the radius is bigger than 1. And the way you kind of work things out is you think in terms of similar triangles. So you have one triangle you can draw like this. So this triangle that I'll draw in red, and of course the height of this triangle is y. The width of the triangle, the base of the triangle, is x. And again, if you remember your Pythagorean theorem, this is a right-angled triangle, so we know that we should have x squared plus y squared equals to r squared. But then there's a similar triangle that's sitting here. We also have this little triangle. Sitting in there. Okay. And we certainly can measure, there's an angle here, theta, and we know how to measure that angle. And because we have that angle, we know what the coordinates of this point are. We know that this point must have coordinates cos theta, sine theta. And now if you sort of think in terms of similar triangles, you say, okay, so that means that the little green triangle, the length of the base is cos theta, the length of the hypotenuse is just 1, and this ratio has to match the corresponding ratio for the big red triangle, so the length of the base x, the length of the hypotenuse r, and so I can solve this now for x, and x has to be equal to r cos theta. Similarly, I have sine theta equal to 1. That would correspond to the ratio y over r, right? The ratio of the heights of the two triangles to the lengths of their hypotenuses. And that tells me that y is equal to r sine theta. Okay, and so this, to some, you could think of this as connecting things back to triangle trig, if you like, right? Cos theta being adjacent over hypotenuse, sine theta being opposite over hypotenuse. But it also tells us that any point in the plane can be identified in terms of how far away from the origin it is and what angle is formed when you draw the line from the origin to that point. I suppose maybe the one exception to that would be the origin itself, where r would have to be equal to 0 and theta doesn't really have any meaning there. But nonetheless, we have this way of using angles to locate points in the plane, and that's going to become important for us when we want to talk about complex numbers in polar coordinates.